have an announcement to pass on, one that I think is actually very important for your education. The Computer Science Co-op information session is coming up in late March, and I highly recommend going to it if you're even slightly interested. The co-op program is like a huge part of, or potentially huge part of your education, assuming you get in. It was definitely a huge part of my education. I learned a lot at my 3 work terms, FarmLink, Ubisoft, and research at the University of Waterloo, and helped me decide where I wanted to go after undergrad, which is to say staying at school, because research was kind of cool. And if you plan on going into the workforce, this will beef up your resume pretty amazingly. Job market sucks, and you need any advantage you can get. And having 3 work terms under your belt, which equates to a full year of work experience, is a really good advantage. I've been told to advertise this a second time closer to the date, so you'll be hearing about this again. So I think that's all for content. No, that's all for not content. Now we're going into the content. Follow along with this exercise. We're going to draw the result of inserting some values into the binary search tree. And we're going to ask, does order matter to the answer? I'm waffling right now while I'm just yapping. Try to think through it on your own. Do you think that the order of the insertions will change how the tree looks? If it does affect how it looks, will it only affect it on a superficial level, like these 2 isomorphic graphs? Or will it actually change which nodes are connected to each other? Which nodes are connected to which other nodes? So 16, 17, 23. To insert 16, we search for 16 and then insert it at the point at which the algorithm failed. So 16 is less than 18, we go left. 16 is greater than 12, we go right. 16 is greater than 15, we go right again. But there's nothing there, so that's where we insert it. Now 17. It's going to go here. I'll go through the full algorithm just to be safe. It's less than 18, left, greater than 12, right, greater than 15, right, greater than 16, right. And 23. Greater than 18 to the right, less than 27 to the left, less than 25 to the right, greater than 21 to the right. So now we have some insertions done. Does the order matter? Yeah, it does. This 23 can be added in any arrangement with 16 and 17 because it's just on a totally different side of the tree than the other 2. But if we added 17 before 16, in this case, the nodes would be basically swapped. 17 is less than 18, greater than 12, greater than 15. And we put it here. And then 16 would be less than 18, greater than 12, greater than 15, less than 17. And it would go here. if the nodes were like indistinguishable from each other, these graphs would be the same, isomorphic, but they're not. Each node has a unique key, the number inside of it. So since node 16 is different from node 17, having the nodes swap like that makes for a meaningfully different graph. Even better, it makes for a meaningfully different binary tree because now the node before, the right child of 15 now has a left child rather than a right child. I'm erasing my artwork because it's done better on the slide right after. And look, the order did matter. I guess the order doesn't always matter. Like I talked about, inserting, say, 23 and then 16 would give you the same result as 16 then 23. But it's not the case that the order doesn't always matter. Negate that statement. The order sometimes matters. Cool. Here's another operation that's necessary for or will be necessary later when we talk about deleting nodes from the binary tree. The successor of a value in the tree is a value that would appear immediately after that value if we listed all the values of the tree in ascending order. So you could imagine all these values being in a sorted array. So it would have 2 first, because that's the smallest one, and then 3, 6, 9, 12, 15, 16, 17, 18, 20. You get it. With that sorted array example, it'd probably occur to you that finding the successor of a value in a sorted array or linked list is real easy. And I hope this one's straightforward too, but it's definitely more complicated. So here's another example to follow along with. We're going to go through this more intuitively, not necessarily following an algorithm, just sort of eyeballing it. And then we're going to use the intuition gathered from just eyeballing it and doing it manually to figure out what the algorithm is. A good workflow for figuring out pretty much any algorithm problem. So what's the successor of 36? I don't know, what's the next biggest value? Looks like 39 to me. What about 21? Looking at it, and it doesn't have any right children, so the next value can't be that. But its parent, 25, is on the right side of it. 21 is 25's left child. So we can see, again, just eyeballing it, not doing anything formal yet, that 25 should be the successor of 21. Now 27, you might be tempted at a glance to say 36, because that's the next node, but it's actually 32, because 32 is smaller than 36. It's between 27 and 36, and just looking at the graph, it's clear that 32 is the one that comes after 27. Nine, we have to go a bit up the tree. No right child, no, and it's not the left child of its parent. Go up, and 12 is the next one. 18, right, it's at the root. hope the gears are turning, and hopefully you're sort of starting to think of a potential algorithm for this. The next value in order is the smallest value that is greater than the current one. So to fulfill those two conditions, we get one that is, or we access the nodes that are greater than the current one, so the right subtree. And then the minimum value of the nodes that are all bigger than the current one is something that we talked about last class. It's the node that you get from going left as many times as possible. Less, less, less. So 18 successor is 20. And finally, with 17, again, we want to find the lowest value that is greater than the current one. But we can't use the same strategy as we used for 18 because it has no right child. Instead, to find the values that are greater than the current one, 17, we need to go up until we find the first, I guess you could call it right parent, node such that the node below it is its left child. We'll think of better terms later. The successors of 17 in this search tree is 18. Let's formalize this. We sort of found ourselves always in one of two cases. Either the node that we're looking for the successor of has a right child, or it doesn't. If the node we're looking at, I'm going to call it X, fine. If X has a right child, then the successor is the minimum value of the subtree rooted at X dot right. So it's right subtree. Like we talked about before, if the node has a right child, then you go to the right subtree and then use an algorithm for finding the minimum value to find the minimum value of that subtree. If X doesn't have a right child, then we get to the case that we saw with node 17 earlier. We have to climb back up through the ancestors of X until we find an ancestor that is the left child of its parent, and then that parent is the successor. I guess the terminology never got any less awkward. You could still say that the successor is the first right parent, but that's pretty non-standard. I think the best we can do is saying that we're looking for a parent such that its child is the left child. In order to make this work, we had to start at a given node and then go up the tree. But that doesn't immediately work because the node class we looked at earlier only had data, left child, and right child. So if you need to take the successor of a node at any point in your program that uses binary trees, you'd have to include a field for a node's parent in the node class. That's not the best thing ever because storing the same data in two different places can get messy and prone to glitches. Like, say you wanted to delete node, I don't know. The binary search tree data structure is kind of too airtight for me to think of a good example of this, but it is absolutely a good principle to keep in mind in general, that you should try to store data in one place and one place only, because maybe you could have a situation where, like, you delete the node 17 and then update the data to say that 17's parent is null, and then you forget to set 15's right child to null. It'd have to be kind of stupid to do that, but like I said, even if it doesn't really apply to binary search trees, it's very important to keep in mind in general. I guess a better example is if you wanted to delete 17 but keep using it somewhere else, like if you're popping it from the tree, and then you set 15's right child field to null, as you should, but forget to change 17's parent, and then when you're working with 17 outside the tree, then you might be misled into thinking that it's part of the tree. I don't know. So I think this is the last big operation for binary search trees. We already have insert and search. And then I think once we're done this, we're going to start actually getting into binary search trees' fatal flaw, because so far, really the only problem with it is that it's a bit more complicated than an array. But I'm getting ahead of myself. The delete operation can get kind of weird, and there are several cases we have to consider, since we have to preserve the binary search tree property in order for any of this to be useful. So for the first case, the easiest, suppose we want to delete value 20. Luckily, it's a leaf node, so deleting it doesn't really have any consequences, per se. You could imagine, perhaps, maybe deleting 27 will require us to do some major re-architecture of the tree. But we don't have to worry about that right now. It's a leaf, so we just access its parent and set the applicable child field to null. In this case, 20 is a left child, the left child of 21, so we set 21's left child to null. Easy peasy. Next up, bit more complicated but not by much, is if the node that you want to delete has one child node. If you just set 6's left child to null, then that'll delete 2, sure, but it'll also delete 3 along with it. And in a lot of cases, you don't want that. Imagine if deleting a node in a linked list also deleted a couple nodes that are adjacent to it. Maybe it would delete its immediate successor too. You don't want that. But we still don't have much to worry about. Since there's just one child, we could move the child to where the parent used to be. And that amounts to making it so the parent, what am I saying? What that amounts to is that in the parent, instead of just setting a child field to null, we set its child field to a different node. in this case, instead of saying 6's left child is null, we say that 6's left child is 3. Ta-da! I'm going to finish this still pretty easy case and then leave the hard case for next week. So for our last example, suppose we want to delete the value 15. 15 has one child, so we could just replace 12's left child, no, 12's right child with 15's only child, 17. It just works. Now, what the heck happens when you delete 27? I don't know. I'll tell you next week. In the meantime, have a good weekend. Hello. Actually, bring your laptop over here.